For problem number 2, we've got a cylindrical capacitor. It has a coaxial cylinder of A and B and has a length L. And one thing it tells you is that it's connected to a source of EMF. Basically, that's your battery. We're going to talk about EMF in a later unit, but you can think of it as voltage. So the charge that's given to the inner cylinder is a positive Q. What that means is that the other side of my cylinder has to be equal and opposite. So the inside is positive Q, the outside is negative Q on the B surface. And that's what makes it a capacitor. So in this scenario, we're going to use Gauss's law to determine the electric field, and we want the electric field between A and B. So in this central area. So we're going to use our Gauss's law, and it's been a while since we've done this, so this is really good review. We take the fundamental principle, and that is equal to Q enclosed over epsilon naught. Our Q enclosed is the inside cylinder, which has a positive Q charge, and the dA is going to be the surface area of a cylinder along its curved surface, not the ends. And so this is going to be 2 pi r times L is equal to Q over epsilon naught. Now, all we have to do is divide that over, and we get our electric field, 2 pi epsilon naught L R, and R is our variable. What I'm going to do here to get rid of all these values and make things easier is I'm going to multiply top and bottom by 2. Why am I going to do that? Because I want to get K as my variable rather than 2 pi epsilon naught in the denominator. So I'm going to multiply top and bottom by 2. That gives me a 2Q in the numerator, and then this 4 pi epsilon naught in the denominator gives me my K variable. So 2KQ over L R. And this is going to be my electric field for within the capacitor. The next thing we're going to do is we're going to use that electric field to find the potential difference between the cylinders. What's nice is that we don't actually have to find the potential at A or at B. We can just solve for the difference between the two, which is the negative integral from B to A, because we always go outside in, of our electric field in that region, which is 2KQ LR dr. I've got a lot of constants here that I can pull out, so I'm going to pull out the 2KQ over L, and now I'm going to integrate from B to A of 1 over R dr. Now, I mentioned this in class that you would need to know how to integrate 1 over R, and it is in your equation sheet. You also should have learned it in calculus up to this point. You're now working on integrals, but the integral is, I'm going to write out my constant, the ln of R from A to B, or from B to A. Now, I know that this is going to simplify out, but I am going to write it out as ln A minus ln B, because I want this negative sign to distribute, and I can write it out as 2KQ over L as ln B minus ln A. And we talked about this in class. An ln property, or natural log property, if you have subtraction, is going to be ln B over ln A. And that is going to be your answer for your potential difference. Okay. Next step is to determine the capacitance of the capacitor. So that's where we take our delta V from our previous equation, our previous problem, and we plug it into our charge over delta V equation. So that's our fundamental principle. This charge right here, which happens to be the same variable, but that is the charge on one side of your capacitor. And they're gonna be equal and opposite values. So you just have to choose a side, make it a positive value, which would be the positive Q, and then that would be your charge. The delta V is going to be the 2KQ over L times ln B over A that I got from part B. And then I just simplify it down. My Q's cancel out, my L goes in the denominator, and my ln B over A can't really simplify any further. So this is a pretty simple calculation now that you know how to do it. Last but not least, we did this in our warm-up also. If I put a dielectric into this capacitor, the equation for capacitance is kappa, so that's my fancy kappa symbol, epsilon naught A over distance. The area and the distance are not changing. So really, my new capacitance is going to be kappa times my original capacitance, and that's what I got for C. There really isn't much to it. I need to write my new capacitance in terms of C naught, and my kappa value, my dielectric constant is 2. So this is your final answer. Easy peasy.